All right, so this section is going to be about network services. We're going to go a little bit deeper into DHCP, DNS, NAT, FTP or file transfer sharing services, your email services, and then your HTTP services. So starting with DHCP, for those of you that aren't familiar with what DHCP is, it's the Dynamic Host Configuration Protocol, usually for IPv4. And it helps automate the assignment of IPv4 addresses, subnet masks, gateways, and other parameters. The alternative to DHCP, or known as dynamic, is static, in which case a network administrator must manually enter in the IP address information and configure all the different parameters on their own. So when a host connects to a network and the DHCP server chooses an address from a configured range called a pool, it then assigns that to a host. And DHCP can allocate IP addresses for a configurable period of time, and that's considered the lease period. So this could vary depending on your home network or large networks. You want to adjust this lease period to be something reasonable. You don't want to set leases out there for 1 year. You typically want to set those out there for, a couple hours or depending on that, maybe a day or two. It depends on how often you change out devices on that network. If it's a corporate network, you may set the lease time down to an hour, which means that they'll have that IP address for up to an hour. It may end up getting renewed, but it will actually release it back to the pool much faster. Whereas your home network, you may have this on multiple days. That way there's no reason to get rid of it. You have plenty of IP address space at your house. So DHCP operation, the list or the order that it goes in here, you start with the DHCP discover. Then you get an offer that's done from the server. You get a request going back to say, I want this particular one. And then the DHCP acknowledge on the way back from the DHCP server. So generally, you're not going to see this. For example, if that offer is no longer valid, it offers it out, but then the client says, yep, I'll take it, and then it's not valid. It will start back over with a discover and go all the way back through. So in the message format that's used for all transactions, these are all encapsulated using UDP. Remember, UDP as a transport protocol is a connectionless and stateless, which means it's just going to send the packet and hope that you get it. Remember, it's kind of analogous to you writing a letter and sending it through the United States Postal Service with no tracking information. These are the different fields that you'll see within a DHCP v4 address. You'll notice you'll see things like the hardware type, the hardware address length, the number of hops, IP addressing that you're going to get through, the gateway address. You can also have these boot flags, which are kind of handy. So within a DHCP server, you can actually configure more than just IP address information. You can actually configure network time protocol. You can configure how to boot the actual system up. So there may not even be a operating system on the client. This is typically referred to as a thing client. And so for like headless type systems where all you're doing is just having a monitor, you can actually boot an entire operating system over the network. It's a little bit of an extension on DHCP, but it is something that DHCP serves. All right, DNS. DNS is going to be your domain name system. This is what's going to help translate between domain names and IP addresses. So for example, if a client asks what is the IP address for Cisco.com, it goes out to a DNS server and then returns that back to an IP address that the browser can actually get access to. Within DNS, there's usually a hierarchy of distributed systems, and they all contain those databases. Those are usually reserved by certificate of authority records, and that way you can make sure that you're getting information from the proper DNS server. The idea is that we can have malicious DNS traffic that can be detected and then inspected with a monitoring service. So I could sit in between you and this DNS server. I could be man in the middle type attacking and filtering out your DNS requests and then sending my IP address back to you so that you as a client is going to try to connect to me versus the actual Cisco.com. So this is what a DNS domain hierarchy looks like. You have what are called TLDs, or your top level domains. These are the ones you guys are most familiar with. So for example, .nets, edus, .coms, all the different ones that are here as TLDs. You have second level domains, which means you're going to have something like cisco.com. And then tertiary is going to be down here where you have your www and FTP and mail and all these different records is what they call these down below. In recent years, there's been quite a bit of new TLDs that have come out here, but those all extend back from a root level domain. So to resolve the name of an IP address, it will check its local DNS cache. So you may know that this is referred to as like the host table, generally both in Windows and in Linux. You have a host file that has records. It will do a lookup there first to see if you have anything statically assigned for DNS. If you do not, then it will go ahead and send a DNS query over to whatever your DNS resolver is. That recursive resolver may need to forward that on up to a higher level domain name server and then go clear out to the root before it comes back with those responses. If the mapping is not found, for example, you can set this over to Google, which is 8.8.8.8, right? You could also have your ISP be giving you an DNS address, and so you may give your request to your DNS at your ISP. Your ISP then passes that up to bigger servers like Google, for example, and then they pass that even further on to get up to the top level domains. Oops, sorry about that. So if a server requires data for a zone, it will request a transfer of that data from an authoritative server in that zone. This process of transferring DNS data between servers is known as a zone transfer. And to do a zone transfer, you're sending all the information from that server back down to the other one. So therefore, the security is pretty high in order to get this DNS information from above, especially if you're getting zone transfer requests. So again, a user is going to type in a fully qualified domain name in the browser application. That query is then sent off to the DNS server. You're then going to see it find something and match it. If it does not have a match, it's going to pass it further upbound and then transfer that information back through the DNS servers to get back to the client. Therefore, the fully qualified domain name, or FQDN, is going to be cisco.com. That's going to get translated out to this IP address here in order for your packets to get further sent out. So if it fails to match through, it's going to go out here. So a client then sends this out to the IP address, and it goes directly out to cisco.com once it's been resolved. On a DNS message, again, it uses UDP. It's typically on port 53 for all the queries and responses. If that response exceeds 512 bytes, then dynamic DNS is used. The DNS protocol communications are a single format. They're generally referred to as a message. And all types of clients will send these queries and responses, error messages, and transfer that record back and forth. So you'll see a bunch of different datagrams built up in UDP with a bunch of different information. These are the different sections in there. So the question is just going to be what's the one being resolved, answer, authority, and moving those on down. Dynamic DNS, some of you might be familiar with this. What this does is allow a user or an organization to register an IP address with a domain name that's in a DNS. That subdomain is then mapped to that IP address of the user's server or home connection. Typically, this is available like for you home users that don't necessarily have your own domain, and so you don't have a static IP address. Therefore, your IP address could change, and therefore you need to update that with the DNS service. And so typically you have these like dynamic DNS providers. This would be one of the main ones, so like DDNS provider. What's going to happen is your user over here has an IP address. You're going to map that out to a provider. And then as you go out and set your IP address, it'll go there. Once your IP address, if it changes over here on your machine, your public, then it will go ahead and update that information with the zone records, and that way that when people look up and find your DNS entry, you can get to it. A lot of times for home users, this is typically used so that you don't have to remember what your IP address is, your public IP. Because that changes generally, unless you're paying for a static IP address from your internet service provider. So this allows you to remember a phrase or a URL address, which is typically easier for people to remember than an IP address. There, if the IP address changes, then you're out of luck until you go find out what the IP address is, where with the dynamic service, it's going to go ahead and update that IP address as soon as it notices a different. And typically this requires a service or a client either installed on somebody's laptop or a server, or even your router can do this type of service as well. The Whois protocol, this is a good page to get familiar with. So Whois is a TCP-based protocol used to identify different domains, like who owns what domain. This is also nice because you just do a search for a QDN and you can find out what comes back. So if we do a search like on Whois, and we get whois.net, which is what you will see on this page here. Give me just a second. Page is acting a little slow here. So you can see the one that they have here, which is the ICANN lookup, and we can look up a domain. So if we look at fhsu.edu, we can see that you have this here. That particular TLD isn't supported by this ICANN lookup. We could do something like google.com. And you'll see these are the domain name registrants that are for this particular domain. So we can see that, google.com, we see the dates, the registration expires out here in 2028. It was originally created in 1997. You can see who the registrar information is. A lot of times this may be personal if it's not obfuscated. So you can see these different requests come in. If we do something like fhsucsc.org, you can see that this is a domain registered for the Cybersecurity Student Organization. It's protected by WhoisGuard. You can see the registrar information that it's done through Namecheap, and you can get some additional information down here as well. So those are nice to be able to look up so you can contact the name of a provider. There usually is contact information here. For example, this one is blocked, but you can, if you're getting abuse from this domain, you can email this particular email address, and then they will contact their client and say they're getting abuse requests. So again, it's just a starting point for potentially dangerous internet locations. It's a great place to go look up. You can use ICANN, you can use Whois, you can use IP domain lookups. So if you're getting a bunch of requests from IPs that you aren't familiar with, you may want to go out and do a search on those and figure out what country they belong to, etc. You guys will do a lab to kind of examine a DNS capture. So you guys will see that within your labs. All right, so NAT is going to be the next service that we're going to talk about. We talked about this a little bit with IPv6 and the reasons that IPv4 is still available. But the idea is that you have IPv4 private address space. And with this private address space, you could have all your devices and resources inside that are on a private address, but they got to get translated to a public address eventually so that they can reach the rest of the internet. So NAT provides this type of translation. Usually a single public IPv4 address can be shared amongst thousands of devices on the inside, each configured with a unique private IPv4 address. This was, again, the solution of the exhaustion of the IPv4 stuff that we talked about. So this is kind of handy. You can just do a simple NAT, go in there. You can have it go out to a single public IP. You could also have a pool of addresses to make that available as well. So NAT configured routers, which is most of your home routers that you have, are typically able to have one public IP address come in from your ISP, and then you have your local IP addresses on the inside. If you end up having more than one IP on the outside, you have what's called a NAT pool, and that means that PCs on the inside will go out various IP addresses, just usually in a round-robin type fashion. The NAT router usually operates at the border of this kind of stub network. So you can see, like, for example, this router here is where NAT is actually done. That way you can have 2 private IP address spaces on the inside. You actually have 3, as this one's connecting over a 10 network in the private address space. You usually want to do NAT up. You can end up doing what's called double NAT. So for example, you will get NAT here, and then you may get NAT here if you needed to, etc. The idea is that you can break up those address spaces. You'll see a video on how NAT works. It's pretty easy to understand once you get going through it. The idea is that you have this inside local address. This is going to be your global outside IP. Your outside local, and then your outside global. This is the way Cisco uses their terminology inside of their routers. It's similar when you work with other routers and devices. Along with NAT, you have what is called PAT, which is port address translation. This is typically known as NAT overload. The idea is that it maps multiple private IP addresses to a single public address, or with the few addresses. When a device gets a TCP IP session, it generates a TCP port, source port, and specifically assigned a query ID for ICMP to resolve. So what does this all mean? The idea is that you will translate inside port ranges with your outside ports that go on the outside. So what this means is I will forward port 80 traffic coming in from my outside to an internal service, say on 10.10, on port 1555. That way I don't have to use port 80 on here, and I can do this the other way around too. But what this does is allow me to share my public IP address and just use multiple ports to translate them to the inside. Some things that you'll see here, you also have things like there's some dynamic services that you may be using inside your home where these devices are doing this randomly and injecting those into your router. That's typically used for not having to manually configure the NAT table with all these different ports, etc. All right, so file sharing, some of the common file sharing services that have been used over the years, you have FTP and TFTP. FTP is just going to allow data transfers between a client and a server. Client runs on the computer. The server is going to be able to communicate, usually through authenticated services. That control connection is going to be lit up to begin with, and then there's a data connection or a second port that's usually used in order to send the data across. TFTP is a real simple file transfer protocol. It runs over UDP port 69. This isn't very common anymore as you're sending plain text or plain information. It's not usually encrypted with TFTP. Even generic FTP, most of this is clear text. You can actually see files being transferred across. And so a lot of times what you'll see today is SFTP. SFTP is going to run SSH over this FTP connection. So you're going to have a nice secure FTP transfer. SMB, or typically known as a server block, server message block, is just a sharing protocol. You might know it as Samba in some other cases. But the idea is that you're going to transfer this across. This is typically within Windows clients. So you have SMB shares and things that you can mount remote network drives to your local system. You could also have printer where you have API access to through the network as well. Messages can start, authenticate, and terminate different sessions, control printer access and files, etc. So that if you've ever done file and print sharing services on Microsoft, you've seen this before. You can share your network-based printer out with the rest of the network. If it was a USB printer, you can also turn on file sharing and print sharing, which allows you to share that printer out with everybody. Then everybody just sends their print request to your PC. Your PC processes that for the printer. You can use things like Windows Explorer. There's other file service protocols out there, but the ones built into Windows is File Explorer or Windows Explorer, and you just mount those files and transfer and copy those back and forth. So you'll do a Wireshark in order to capture an FTP and a TFTP session. Email services. Email, I think everybody's familiar with that in this day and age. Email's pretty popular. When it first came out, we were using things called POP and SMTP, or Simple Mail Transfer Protocol. You also had the Post Office Protocol, and now you have things called IMAP. A client typically, when you're sending email, you're using SMTP protocol in order to send that email. And then once it gets over to a mail server, you typically either interact with that either through IMAP or POP3. POP3 has definitely gone by the wayside, but it's still out there today. The difference between IMAP and POP3 is POP3 will collect all your emails, and then you as a client download all those emails from the server. Once you download them from the server, they're gone. They're no longer on the server. Which means back in the day when we had email services before things like Gmail, what we had to do is we would connect with a client, whether that was Microsoft Outlook or Thunderbird or whatever email service we were using back in the day. You would download that email, and once it's on that client, it's there, which means if I go to another computer, I can't get access to those messages. It's on whatever client I downloaded them to. So back before we had things like smartphones, etc., POP3 was a real nuisance, especially if you had multiple machines. So a lot of times you'd have to leave copies on it on the server, which means that your server was going to fill up. You only had limited amount of storage, etc. With IMAP, all the emails stay on the email server itself. You're just interacting with the server through the IMAP protocol. And the benefit with this is I can connect my phone, my laptops, my desktops. Everybody can be connected to the same email account. And it's going to send and receive emails, but store everything on the server. And so this is your typical Gmail service that most of you are familiar with. So again, SMTP is when you typically send an email out. This is going out port number 25. It's a good port to memorize. So if I want to send email out, it goes through SMTP, goes through to a server. Again, this usually ties with POP3. I'm going to send it through SMTP. That goes over here from the server to the client's POP3 server. And then a recipient is going to use POP3 in order to download that from the server. So you see POP3 here. That's how that message is going to get from here and send it on to the recipient's box. POP3 runs over port 110. So if you see port 110 open, you more than likely have an email client out there listening. IMAP, as we said before, you're still going to send through SMTP, but IMAP is just another way for you to interact with this particular client so that those files are stored up here and organized on the server itself. When they delete that email, the server will synchronize that action and delete the emails from the server as well. All right, one of the last ones that we're going to talk about today is HTTP. Most of you guys are familiar with standard hypertext transfer protocol or hypertext markup language. This is usually the web address or the URL that you type into a browser. That web browser establishes a connection with some web service or server, and that's using HTTP. You also are probably familiar with HTTPS, which is the secure version of HTTP. Most items today are all using HTTPS, even if you're not logging in or anything like that. They all have some form of verification. So initially you're going to start with HTTP. You're going to go out here and try to do a request to Cisco.com. Remember that that request is then going to get translated from DNS back to an IP address, and then you're going to use HTTP to a quote IP address in order to pull a certain website. So as you see here, you're going to get a client requesting a particular address. They do that with a GET request inside the HTTP protocol. And it typically asks for index.html. That's the basic page that most web services have. Now, there could be some variants of this, and your web server that you use will all depend on what core page or landing page that you're going to get when you first get a request. It's going to take the HTML code. So if you haven't seen HTML code, it looks like this here. You usually have a header and then your title, and then you get into the body or the contents of your message. That's all going to be sent back, sent with the HTML code over to the client, and then that's going to get formatted based on the browser that you use. So if you use Internet Explorer or Microsoft Edge or Google Chrome or Mozilla Firefox, it may or may not format that information a little bit differently here. Even though it's an open source code, typically that output on the page is going to vary between browsers. So the URL, when you guys always look at URLs or you specifying something in there, you typically have the schema protocol, HTTP or HTTPS. Typically on HTTPS, this is going to be on port 443, where port 80 is your standard HTTP. However, if it's in a non-standard port, you're going to see the domain and then colon, a port number. This means that you have a web service running on a non-standard port. You then have a path, which is going to be this folder here. The moment that you see a question mark, this is typically going to consist of key value pairs. So for example, doc ID is equal to this, format is equal to that. And then anytime you see a pound sign with numbers or anything after that, this is usually additional information that's being sent in that URL request so that it pulls back certain files. So for example, in this one that we see here, it's going to connect with HTTP to example.com on port 8080. It's going to go to the sounds directory and retrieve the one with the ID of 973285 in the format of an MP4 file, which is a sound file, and then start at position 0 minutes and 0 seconds. So start at the beginning of the file. And you guys will see this too if you play with YouTube or anything like that. You'll get these URLs and you'll have similar results in this. So the different methods or the different requests that are sent within HTTP, you typically start with a GET request. If you're going to send information, you fill out a form, etc. You're going to have a POST request. You are posting things to the server. You have puts, deletes, options, and different connects. These are, based on other services that you may be using on that website. HTTP status codes, there's a couple that you should be getting familiar with. Most of you have seen this. So if you go to a website that doesn't exist, typically you see the dreaded 404. You may be seeing some other errors or something like that pop up. Maybe a server 500 error, which means that the server has an issue. 400 errors or that the client has an issue. 100 are just informational. If you get a straight 200, this just means everything worked correctly. And then a 300 is going to redirect you to another website. So you may have it being redirected to another URL. As you see here, 403 is forbidden, means that you don't have permissions usually to view that source. And 404 means that it's just not found in general. So there's a new protocol called HTTP 2, which is used to improve the HTTP performance by address latency, etc. within 1.1. Uses the same message format, same status codes. The main features that a cybersecurity analyst need to be aware of are being able to multiplex streams across there. So typically you used to set up TCP sessions, as you see here, one for each source or resource that you're going to be filing. So whether that's the HTML page, a picture, JavaScript code, it had to set up individual TCP sections. Now that's being multiplexed over a single TCP connection. A lot of this is typically because you want to do this in a secure fashion. It also limits the amount of TCP sessions, which therefore limits the amount of ports that have to be open on a client. You can just open one single port and transfer that information back and forth. As we talked about, HTTPS is the secure version of HTTP. It typically uses authentication and encryption to secure that data as it goes back and forth. As far as securing that, there's a couple different protocols you can use, either SSL or TLS, in order to encrypt that data and send that across there. And then you can use HTTP over TLS or application layer protocol negotiation to figure out which version of TLS you're going to use. Typically today you want to make sure you're using at least 1.2 or newer. Otherwise you can get your information decrypted pretty easily. Confidential information should be transmitted over HTTPS. So if you're logging into your bank account, etc., you should always check to make sure that you have the little padlock up in there. So for example, this Zoom, I can click on this padlock and see my connection is secure. And if I look at the URL address, we'll see that I have HTTPS up here. I can then also go in and look at the certificates and make sure that they're valid certificates. So you guys will go through in Wireshark, and you'll also be able to analyze the difference between an HTTP packet as well as HTTPS traffic. So to summarize today, these are just different network services that you guys are going to encounter, particularly in Wireshark. That's why you guys are working with it. So as you're trying to analyze what services are going across your network and identify ones that maybe shouldn't be there. For example, if your network should not have SMTP and POP3 running on it, but you see those ports open, you may want to find out why there's an email client running on that system and why it's using old, outdated protocols. So DHCP operations, you do a discover, offer, request, acknowledge, and then a NAC. You also have DNS, which will resolve names to IP addresses. NAT, which is going to do network address translation of private IPs to public IPs. Typically, this is done at the border of the stub network or wherever you're connecting to your ISP. You can also use PAT, which is known as NAT overload. This just allows you to use multiple private IPv4 addresses to a single public IPv4 address or maybe a couple addresses, but uses port translation so that you can use multiple ports on the inside. FTP was used to transfer files between clients and servers. At TFTP, again, not used much today, is just a simplified protocol that's used over UDP. Note that it is over your UDP, so there's no connections, there's no assurances that you're getting those files. We talked about email clients and the difference between SMTP, POP, and IMAP. Remember that SMTP is used for both. This is your send protocol. Your POP or POP3 is what's going to be used to download messages from a server if you're using an older style protocol. And then IMAP, the messages are stored on the server itself. Think IMAP is equivalent to Gmail. You have your web browsers, your web servers, how they interact. Typically, HTTP runs on port 80. You have a couple different methods that you can use by that protocol. Most of the ones you're going to use are GET and POST, but you also have puts, deletes, options, and connect. Your standard status codes, know that you have the 100s, 200s, 300s, 400s, 500s. Remember that 500s are server errors, 400s are client errors, the web browser issues. Like a 403 means that you don't have access. A 404 means the file's not found. Typically, this is a 500 error from a server if you're having issues. 300s are going to be redirects, which means you went to a website, but it's redirecting you to another one. 200 is a OK status code. That means that everything went smoothly, and then your 100s are just going to be informational. HTTPS is used for secure transmissions, and that's going to use authentication and encryption. Note that those are two different things in order to verify and send secure data between the client and the server itself. And that covers network services for today. Make sure you guys have a chance to go through all your labs and explore those. That way you get familiar with those packets, particularly later on in the class when we start having to examine traffic flow on the fly. You'll want to be able to pick out what packet is what. Thankfully in Wireshark, it will highlight these with different colors. So you definitely want to be familiar with that tool in order to identify that traffic.